Welcome to the second lesson on magnetism and electromagnetism. My name's Mr. Pratt, Director of Science, and we're going to start looking at magnetic fields this lesson. For this lesson, you're going to need a pen, some paper or an exercise book. Unless you're needing to watch this video on your mobile phone, turn it off or put it on silent, turn it over, try and avoid all the distractions that you can. Into the starter then. So you should recognise that diagram from the previous lesson. I want you to tell me what the difference is between a permanent magnet and an induced magnet. List as many magnetic materials as you can and complete the following. Like poles blank, unlike poles blank. I'll give you 2 minutes. Minute gone. Just be finishing off then. Let's see how you've done. Mark what you've got, correct it if it's wrong, or just add if you're missing something. So, question 1, what's the difference between a permanent magnet and an induced magnet? This refers to the diagram. Your permanent magnet is the magnet with the north and the south marked red and blue. That's a permanent magnet. It stays a magnet. It's always magnetic. But an induced magnet is a magnetic material that will become a magnet only when it's in the magnetic field, so when it's touching that magnet. So they're only magnetic for the period of time that they're next to the magnet. Question 2, if we go with the 3 elements, iron, nickel, cobalt, if you've got an alloy, a mixture of metals like steel, that will be magnetic because it contains a large amount of another element that's magnetic. Question 3, like poles repel and unlike poles attract. So the outcomes then. First outcome is to be able to draw a magnetic field produced by a permanent magnet. So we'll draw what the field, which shows us the forces around that magnet, looks like. Common exam question. And the other outcome, use a magnetic field diagram to describe and explain the magnetic forces around a permanent magnet. Let's start with something that you will have heard of. The Earth has got a north and south pole. So I'll just give you 30 seconds. Just think, what could this mean? What does that actually mean? We've got the view of the Earth from above the South Pole on the left and from above the North Pole on the right. Okay, so word pole means end. So the Earth's a sphere, so it doesn't really have an end. But because it rotates, it spins on its axis. You can see on these diagrams here, it spins on its axis, but it has a magnetic field around it. It's as though the inside of the Earth has a massive permanent magnet inside. Now, interestingly, if you look at those two, the North magnetic pole is actually at the South Pole of the Earth, which is why when you get a compass, it points to the north. So the North Pole of your plotting compass is pointing to the magnetic south. So it follows those lines. So as we move through this lesson, we're going to explain what these lines mean and how we actually see them, how we can see that they're there. So the Earth's like a giant magnet. It produces its own magnetic field. Some planets do, some planets don't. The reason the Earth does is because it contains a molten iron core that's rotating, and it's that's generating the magnetic field. So compasses always point north. They're pointing to what we call the North Pole, the Arctic. Also, surprisingly, that magnetic North Pole and South Pole, they move. So they will actually move different places. At the moment, it's moving quite quickly from North Canada, where it was, towards Siberia. Some animals, including homing pigeons, can use this magnetic field, and they can, a part of their brain can actually sense it, and it can use them to work out which way it's pointing to fly back to its location. They're also used by a lot of mammals in the sea, including whales as well, that can follow the magnetic fields to find their way across the sea. So we're going to look at two demonstrations now. So the first demonstration is using a magnet and some iron filings to see a pattern that's caused by the magnetic field. And then, more importantly for you, the second demonstration, we're going to use a plotting compass that you'd use to find your way around using a map, to draw the magnetic field and put arrows on it to show the direction that it's pointing. Again, that's a common exam question. That's the more likely question that you're going to get in your exam. So what we're going to do, I'm going to show you a clip of me doing both those demonstrations. After each clip, you need to record the method that I've followed. In other words, explain how I've done that demonstration in 3, 4, 5 steps.
So first of all, we'll have a look at the magnetic field around a bar magnet, but we'll do it in the way that you might be familiar with. You may well have done this lower down the school. Just going to put a piece of plastic over the top. You'll see why. I'll just make tidying up slightly easier. And I've got some iron filings. So they're just tiny, tiny bits of iron. Iron, of course, is one of the magnetic materials with nickel and cobalt. And I'm just going to sprinkle it around the magnet as carefully as I can. The key is to put enough on so you can see the pattern around it, but not put too much on, so know when to stop. Okay, I'm just going to give it a bit of a tap. Okay, so what you should see is we've got quite a lot of the iron filings are sticking to the North Pole and the South Pole. That's because they're the strongest parts of the magnet. So we say the magnetic field at the poles is the strongest. So if we just look at the North Pole, then what we've got is lines forming going out, and these lines then will come round and go to the South Pole. So we've got lines like that, lines coming out there, lines coming out there, and we'll draw this in a while. So that's one way of just having a look at the magnetic field pattern. We use the word field just to describe forces in different places. So if we're talking about a magnetic field, we're talking about the force due to magnetism around this permanent magnet. If we're talking about a gravitational field, we're talking about how gravity affects things in the Earth, around the Earth, or around any planet or star. So that's that pattern. So try and remember that and draw it in a bit. Take that off. And then I'm going to very carefully, I hope, pour it back into the bottle. And then I'm going to just do it again, but I'm going to put two north poles facing each other. That's as close as I can get them, because of course two like poles repel. I'll just put this back into the bottle. And then put it back over again. Now, because we've got two north poles, two like poles facing each other, the force around those should cancel out. So what we should see is a lack of magnetic field in that space, and we should see that by no iron filings settling there. So if I start with there, should get the same pattern as we did before to start with. And we should get the same over here. Let's try in the middle then. Got a little bit stuck in the middle. So what we've got now, we've got the magnetic field north to south, but in this gap, it's cancelled out. So we'll do a diagram of the magnetic field lines later where we can actually show that using field lines.
Okay, I'm going to give you 2 minutes now, and I want you to record a method from what I just did in demonstration 1 and explain what the pattern tells us about the magnetism. Okay, just be finishing off.
So that's called a plotting compass. All it is a very small permanent magnet that's just sat on a pin so that it can rotate. And what that will do, it will line up with the Earth's magnetic field. So at the moment, it's pointing probably a bit difficult for you to see. It's pointing in that direction, which in my kitchen is north. North, east, south, and then west. And I've got lots of these. And all of these, because I've checked, all point in the right direction, and then they'll all point north. So I've got lots of them. So what we're going to do now, we're going to use those to plot the magnetic field around a permanent magnet. But this time we're not just looking at the pattern, we're looking to get a direction and more detail. So if an exam question asks you how you would plot a bit like a graph, the magnetic field around a permanent magnet or anything else, you do it this way using a plotting compass. So what I'm going to do, I'm going to put loads of these. If you were doing this in class, you'd probably just have one and you'd move it around. So what I'm going to do is I'm just going to get loads of them. I'll put them in some sort of pattern in a minute. Be looking at the way that they're facing now. So this permanent bar magnet, the magnetic field here, close around it, is a lot stronger than the Earth's magnetic field. So we can ignore the Earth's magnetic field. What these plotting compasses are now going to show you is the direction of the magnetic field around it. So I'll just take them slightly out of the picture a bit. Okay, so what I'm going to do now, I'm going to take each one off and I'm going to put down an arrow representing the way that it was pointing before. A bit of a pattern forming there. Put one there. And if I carry it on further out, choose one, make it less complicated. So I've got that pattern over here. Okay, just going to get these out of the way. I'm just going to go with one now. So, what we've got arrows coming out of the North Pole and arrows going in to the South Pole. I'm going to join these up now. Okay, let's carry it on. Carry it on. Round there. Okay, so now we've got the magnetic field drawn. So drawing something like that will get you 2 marks on the exam. But points to note that make it a bit more useful to you. The magnetic field is strongest where these field lines are closest together. So you can see that the magnetic field is strongest at the poles. We fill in those lines there. You can see the lines are getting closer together as they go into the poles. Down the sides, you can see that the lines are spread further apart. If I were to draw another one in, you can see out here, it would be getting weaker. So, where the lines are closest together, magnetic field is strongest. Where the lines are furthest apart, the field is weakest. It'll get weaker and weaker and weaker as you go further away from the magnet. And the magnetic field lines go in a direction as two, so you need to mark a direction, and that direction is always from north to south. It's the way that you'd say it, and in alphabetical order, the magnetic field lines go from north to south. So don't forget to mark your direction. What I'm going to do now is something similar. I'm going to flip it over and we'll put a north and a north close together. I'll get them as close as I can without them repelling each other. That was too close. So pop one on there, and it's pointing to the south because we know the magnetic field lines go from north to south. So if I go to the other south, it's pointing to south again, so they're going to go in like that, in like that. Now here they're coming out of the north, but because in this point, if I could mark a point, I'll put a dot exactly between these two north poles, assuming that they're the same strength. That point there would have no magnetic field in it because it's cancelled out from the two north poles repelling each other. So the magnetic field looks very similar, but it's a bit squashed. So south side doesn't really look any different, but it's squashed north to south, north to south, here, with no magnetic field in the middle, which is why if you put iron filings there, they'll disappear and jump to one pole or the other. So we said where the magnetic field lines are strongest, flip it back over, go from north to south. Where the magnetic field lines are strongest is where the magnetic field is strongest. So if I just get a paper clip and throw it, and I'll try and throw it in the middle. Nope, doesn't land in the middle. Let's try again. No, doesn't land in the middle. Oh, now that stopped there. Most likely to end up at one of the poles, and that's because the magnetic field lines are closest together at the poles. That's because the magnetic field is strongest there.
Okay, now I want you to record a method and explain what the pattern tells us from demonstration 2. 2 minutes. Minute left. Just be finishing off. So here we've got a model answer for the first demonstration that I did. So I just want you to have a look what you've written. You may not have had 5 steps. That's not a problem. You'd probably be talking 3 marks maximum for a question like this. So we've got a piece of paper on top of the magnet. I used a piece of plastic. You can use either. Slowly sprinkle the iron filings on. Shake the paper. I just tapped it just to allow the iron filings to move into the field, and then sketch your pattern, and then you can put your lines on that pattern. So you decide what do you think you've got out of 3 marks for that first one. More importantly, because it's more like to be on the exam, this is the second demonstration that I did. So again, the start's the same, piece of paper or piece of plastic, but this time no iron filings. We're using a compass. We put a compass on it. We look at the way that the compass is pointing, and then we draw an arrow where the compass is, saying which way that it's pointing. And then you just move your compass round, or if you've got more than one compass, you can have lots of them around, and you mark on the direction that the compass is pointing. Then you just have to link up the field lines with a pencil all the way around. So again, mark out of 3, you decide what you've got. So just to summarise, so a magnetic field is a region, it's a place where we've got forces. So a magnetic field is just an area where we've got magnetic forces. And these forces will act on other magnets, or they'll act on other magnetic materials. So the field diagram is just a way of visualising where these forces are by using lines and arrows. And the lines always go from north to south, alphabetical order. Okay, not only does that field diagram show us the direction of the magnetic field, it tells us that where the lines are closest together, the field is strongest. So that's at the poles. As you move away from the poles, the field lines are further apart, so the magnetic forces are weaker. And as you just move away to the side as well, the lines get further apart, so the magnetic forces get weaker. Strongest magnetic force at the poles, weakest out there at the sides. So I'm going to give you 2 minutes now, might give you slightly less actually, and I just want you to quickly sketch from memory now. Don't look at what you've done before, where those magnetic field lines will go. Don't forget you need lines, and the lines shouldn't cross, and you need arrows on those lines. Okay, I think I might have been a bit generous with the time. Should have got your lines drawn on now. You shouldn't cross either. and then add lots of little arrows onto those field lines, remembering they're all to go in the right direction. It's also worth checking that you've got them in the right direction. You've not got one pointing the wrong way, so just double check. Then just say where the magnetic field is strongest and where it's weakest. Okay, I'm going to say that's time's up there. So it should look like that. Make sure you've got your arrows on, no lines crossing. Strongest there. Okay, the diagram on the right is one that I did demonstrating with both iron filings and the plotting compass. The one on the left I didn't. So let's look at the one on the right first. We've got two north poles next to each other. So because those two north poles are repelling each other, we have an area in between them where there's no lines because there's no magnetic field, so it cancels out. If you had to do a diagram like the one on the left, all you've got to remember is that magnetic field lines go from north to south, so they'll go across from north to south. They're almost parallel in the middle, but they're spreading out as you get further away. If you just remember north to south, you'll be picking up marks in the exam. Right, what we've got now is 7 diagrams. There's a mistake in each of the 7 diagrams, and I want you to identify what the mistake is and then correct it. And then when I've given you 4 minutes total, I'll put some answers up and you can self-assess. So something wrong with each one, say what it is and sort it out. Okay, you should probably be on number 3 at least now. Okay, you've had half your time, so you should be past halfway. Okay, you should be on either 6 or 7 now. Okay, just be finishing off. Okay, I want you to self-assess then and correct what you've got. So the first one, number 1, they've got aluminium and copper attracted to the magnet. They don't, because they're not magnetic materials, but nickel and cobalt are. Number 2, it says there on the diagram that 2 south poles are attracting each other. They don't, because like poles don't attract, they repel. So just replace the word attraction with repulsion, or swap one of your magnets around. Number 3, straightforward, magnetic field lines always go from north to south, alphabetical order. They've done the wrong way around, so you just need to reverse every single arrow. Number 4, they've got on the diagram that the field lines have gone from the North Pole on the left to the North Pole on the right. They don't, they always come out of the North Poles, so you'll end up with that gap in the field lines where there's no magnetic field, because there's no magnetic force, because it's cancelled out in the middle. Number 5, well, they've not completed the magnetic field, you just need to complete it and finish it off. You'll notice that the lines themselves, if you ignore the arrows, are symmetrical. So when you draw it, try and make it look symmetrical. Number 6, here they've got the magnetic field lines coming out of the north. That's fine, but they've also got field lines coming out of the south on the right hand side. They should be going into the south, which means that in the middle there, the magnetic field lines go from the north to the south. And number 7, the paperclip's an induced magnet. Now, induced magnets will only set up other induced magnets and you'll get attraction. A paperclip can't end up repelling something. It's not a permanent magnet. Okay, the plenary. Now, we've not even looked at magnetic field lines around electromagnets. Now, this is leading into the next lesson where we're going to have a look at how electricity can produce magnetism, which is why the topic's called Magnetism and Electromagnetism. But what you should be able to do is use the knowledge from this lesson to describe the field lines and what they actually mean, what they look like and what they mean. So describe and explain. And then number 2, I want you to work out which end of that electromagnet becomes a north pole and which becomes a south, and you should be able to do that from what you already know about magnetic field lines. I'll give you 2 minutes. Okay, a minute left. just be finishing off then. Right, question 1. Let's describe first. So we're just describing the lines, the field lines. So we've got the field lines are very close together at A and B. They're the ends, the poles. So the field lines are close together there. They're more spread out at the sides, and they're more spread out as you move further away from the electromagnet. So we've just described, we've explained nothing. Explain then. So, explaining, because the lines, the field lines, are closest together at the poles, the magnetic field is strongest at the ends, at the poles, weaker at the sides, and weaker as you move further away. Question 2. Which pole is north, which is south? Well, it's 50-50, isn't it? But if you look where the field lines are coming out, remember, we already know, and we must have said this 15 times in this lesson, the field lines go from north to south. So that means that A must be the north and B must be the south. So if you complete the Google quiz now, this will be automatically marked. So we've got a summary. You can record this if you've not got these diagrams already. You may well have the permanent magnet with the magnetic field lines around it already. So we've got a method for plotting the magnetic field around a permanent magnet there. We've got a diagram of the Earth with magnetic field around it, and we've got the field lines around a permanent magnet. So write down what you want to record, pause the video if you need more time, and I'll see you next time for the third lesson on magnetism and electromagnetism, and we'll be looking at some different magnetic fields that we can create with electricity.